Well, hello there. Today is the second topic on the AQA topic 1 of paper 1, particles and radiation. This topic is about what makes the nucleus stable and unstable and why the nucleus emit different kind of particles. So today you'll be learning about three particles: alpha, beta, minus, beta plus, gamma radiations, and also what keeps the nucleus together. So there's a new force we'll be talking about today, that is nuclear force, but that in a minute. But first, let's just recall what is this electrostatic force of repulsion. So you have learned this in your earlier classes that when there are same charges, if you have a positive charge and another positive charge, for example, a proton will always repel another proton, isn't it? So this is going to go in this direction, this is going to go in this direction. So there's a strong electrostatic force of repulsion between two protons. Or if there are neutrons, because it does not have any charge, there's no force between neutrons and protons. Now, when we move on to the nucleus, which is inside an atom, just trying to make a model of atom here. So let's say the smaller circle is the nucleus, proton, neutron, proton, and neutron. So what is happening between these two protons is, according to our understanding, there should be a repulsion force between these two protons. And because of this repulsion force, the particles should go away from each other. Then how come a nucleus, a very small nucleus, which has so many protons, sometimes if I take an example of uranium 92, so it has 92 protons inside a small space of around 10 to the power minus 15 meters. So close, so many protons, so repulsion should make it unstable. But most of the atoms are not unstable. So what is keeping those atoms together is this new force, which is called nuclear force. So first, let's understand what are the properties of this nuclear force. First, it is attractive. Second, irrespective of the charge. Okay, it does not depend on the charge of the particle. So it is independent of the charge. So if you have a proton neutron or a proton proton, it will have a same attractive force between the two particles. The only thing it is dependent on is the distance. It's that's why it's also called a short range force. That means it is dependent, it exists only when the distance is of the order of 1. Now you need to know this for your exam board. FM, this is a short form for femtometer. Okay, and 1 femtometer is 10 to the power minus 15 meters. So 1 femtometers to 3 femtometers. The minute the distance go higher than 3 femtometers, the nuclear force becomes weak or stop existing. Always attractive. If the distance is in the range of 1 to 3 femtometers, typically 1 femtometers, the force is always attractive. Now imagine inside the nucleus you have neutrons. Okay, forget the neutrons for a minute. If you have two protons, they are repelling each other by electrostatic force of repulsion. Okay, so they're trying to push each other away. So electrostatic force of repulsion, which depends on the charge. And then they are attracting each other by a force of attraction, which is nuclear force. So if it is a stable nucleus, the nuclear force is balanced by electrostatic force of repulsion. Okay, so the new thing that you learned today is about the nuclear force. It's always attractive, whether it is between proton-proton or a proton-neutron. It is independent of the charge, will not depend on the charge. So unlike the electrostatic force of repulsion, which exists only when there's a charged particle, nuclear force is independent of the charged particle. And the limitation is for this force to exist, is that it is dependent on the distance. The distance goes beyond 3 femtometers, it stops existing completely. Okay. Now, obviously, then what keeps the nucleus intact? So, first, if your force of repulsion and nuclear forces are balanced, the nucleus would be intact, would be stable. But then, if the nucleus size becomes too large, the size of the nucleus is too large, that the nuclear force becomes weak, it becomes unstable. So, a large nuclei would make it unstable because the nuclear force would become less. Sometimes it has too many protons. Okay, so if it has too many protons, so again the electrostatic repulsion force dominates, and then again the nucleus becomes unstable. Third, sometimes if it has too many neutrons, okay, so the nucleus becomes heavy, and then also the nucleus becomes unstable. So if it is large, too many protons, too many neutrons. The minute you think that is becoming too much knowledge, pause, try to recap in your head, and then move ahead. Now, if the nucleus is unstable, it is going to start emitting some particles. It is trying everything in the universe, tries to come in a situation which is a stable situation. This nucleus cannot live like this. So if it has to become stable, what would it do? If it is very large, okay, let's just go back. If it is a large nuclei, it'll try to become a smaller. If it has too many protons, it'll try to emit protons and get rid of some protons. If it has too many neutrons, it'll try to get rid of some of the neutrons. Okay, now how that happens, that's what leads us to our particles. So this is how it becomes stable. Alpha decay generally happens if the nuclei is too large. Okay, a larger nuclei would emit alpha particle. A beta minus decay occurs if it has too many protons. Beta plus, too many neutrons. Okay, let me just write here. Too many neutrons, too many protons. And then, of course, the gamma decay is when you have an unstable nucleus. Okay, so you have two, I think I've written it all the way around, and this is when your nucleus is highly excited, it's an excited state, or it has too much energy. Okay, I'll explain you this in a minute. Okay, let's just see now. So alpha decay happens if an alpha decay happens because it was nucleus is too large, it's trying to become smaller. It's trying to become smaller by emitting out a new alpha particle. Okay, so the alpha particle is nothing but the helium nucleus. So this is helium nucleus. Okay, so when it converts into the smaller nuclei, it becomes more stable. Now what you need to know for your examples is how many, so when it emits an alpha particle, what is the atomic number and mass number of the new particle? That's what you need to know, and that's what we're going to practice in a minute. Alright, so let's just see here. So as you can see, if I've used the symbol equation first. So if you see the symbol, the Z shows atomic number. So after emitting an alpha nucleus, the atomic number decreases by 2 and the mass number decreases by 4 because the alpha nucleus would have a mass of 4 and charge of 2. This uranium U-238 nucleus, which has 92 protons, after emitting an alpha nucleus, it has changed into a thorium of 90 atomic number and 234 mass number. So a larger nuclei has converted into a smaller nuclei by emitting an alpha particle. So what you need to remember from here, that whenever an alpha particle is, alpha is sometimes written like this, or it is written like this. You've done this in your GCSE. So whenever an alpha particle is emitted, atomic number decreases by 2 and atomic mass decreases by 4. That's what we need to know. But don't worry, we're going to practice some exam questions. It'll make more sense. Now, if it is a beta minus decay, as I told you earlier, if it has too many neutrons, it would change into, it would become stable by emitting neutrons. So it doesn't emit neutron. What happens is a neutron decays into a proton, because it was too many neutrons. Now it has one extra proton, and it emits one electron which comes out of the nucleus as a beta minus. So beta minus particle is nothing but E minus, an electron. So if an exam question asks you what particle is similar to beta minus, it's nothing but electron. And this is called antineutrino. We'll learn about this in the next video. So if a neutron decays into a proton and a beta minus particle and antineutrino. So you can see here the carbon 14 decays to become N14 and a beta minus and antineutrino. Now let's see what's happening. Now this is needed for your exam board. What's happening to atomic number? As you can see, the atomic number increases by 1. See, because the neutron has changed to a proton, and atomic number is nothing but the number of protons. So atomic number has increased by 1, but mass number has not changed. Remember, the mass number is nothing but the number of neutrons and protons. The number of neutrons has decreased, but the number of proton has increased by the same. So the mass number remains same, atomic number increases by 1, and electrons are emitted, which are called as beta minus and antineutrino particles. They're nothing but just energy particles, but we'll just study about them later. Now beta plus decay happens when it has axis of protons. So you can see here, axis of protons, it changes to a neutron. Proton is changing into neutron, hence again no change in the mass number. A positron, this is called positron. We'll learn more about these particles in the next video. So positron, and this is called neutrino. A proton decay emits a positron, which is called beta plus, a neutrino energy particle. Now what happens in a beta decay? Mass number remains same. So mass remains same, number remains same, and atomic number decreases by 1. Okay, number decreases by 1. Now see how you can balance it. See, this is 5 and this is plus 1. So 5 plus 1 is 6, and this here is 0. So actually, if I want to write it in a balancing form, I should be writing like this. 6C11 gives 5B11 plus 1 E0 plus neutrino. This one has no charge, no mass. So plus 1, 5, 6, 11 plus 0 is 11. If I want to write the previous one, the beta minus, how I can write this is, I can write like this. 6, 14 gives 7N14 plus minus 1 E0 plus antineutrino. So 7 minus 1 is 6, 14 plus 0 is 14, and this is 14. So you just need to balance. So now the exam boards are only expecting you to remember what happens in beta minus, beta plus, and alpha decay, what happens to the mass number, what happens to the atomic number, and why that happens. Now the gamma decay happens whenever let me just go back. Here. So in alpha decay, when this one has emitted an alpha particle, it goes into an excited state. Okay, so the nucleus, after emitting beta minus, beta plus, or an alpha particle, goes into an excited energy state. And then it comes back to the lower energy state by emitting energy in the form of gamma radiations. So whenever gamma radiations are emitted, as you can see, there's no change in the mass number and there's no change in the atomic number. Only thing is this asterisk mark here, this shows a meta state. You don't need to know this, but just to understand what is happening. So this is kind of a meta state. Meta state means it's an unstable state. So it becomes from an unstable to a stable energy state by emitting gamma radiation. So this is a symbol for gamma radiations, which is nothing but high energy electromagnetic wave. No change in mass, no change in atomic number. One of the exam question is something like this. This is obviously a 1 mark question. Now, an unstable nuclide is decaying to nuclear T through a series of alpha, beta minus decays. Which statement is correct? Okay, let's just see. So if I'm going to just do it, if this is X and this is Y, okay? So the atomic number after alpha becomes -2 and the mass number becomes -4. After beta minus, okay, let's just go back. What happens after beta minus? The atomic number increases by 1 and mass number remains same. So going back, atomic number increases by 1. So it is x minus 2 plus 1 would become x minus 1. This would remain 1 minus 4. Another beta minus. So -1 plus 1 becomes x. This would remain 1 minus 4. Another alpha particle, x minus 2 and y minus 8. Let's see. Which statement is correct? P and S are isotopes. This is P and this is S. Same atomic number, different atomic mass. Yes, it is. It is right. P and S are isotopes because they have same atomic number and different atomic mass. Let's do the second one. Q and T have different proton numbers. This is Q and this is T. They have same proton numbers, isn't it? X minus 2. So that's not right. Q and S have different nucleon numbers. Nucleon number would be another name for mass number. Say number of nucleons. So let's see. Q, this is Q and this is S. Sorry. Q and S have different nucleon numbers. That's not right. They have same nucleon numbers because they have same mass numbers. Okay, Q and S. So this is also wrong. R has a great proton number than P. Where is R? R and P. No, R has less proton number than P. So that's also wrong. So just seeing what's happening. Okay, let's just see this one. This is an unstable nuclide. Okay, so this is your hint. It is going to start emitting something. Radioactive decay series, it decays by emitting alpha, and next two nuclides in the series emit beta minus. Which nuclei is formed after 3 decays have taken place? So I'm going to write like this: 92 thorium 232 emits alpha. Okay, I don't know what's going to happen here. After emitting alpha, it will be 90 and 228. Okay, this one then would emit a beta. It would become 91. Atomic number increases by 1. And then another beta particle, 92. This would remain 228. This would remain 228. So as you can see, I started with a 92. I ended up with a 92. So if it's a, no, sorry. Okay, it's 90. 90, 88. Okay, that is, I really need to get my number of my specs changed. So this becomes 89 and this becomes 90. So it started with a 90, ended with a 90, same atomic number, different atomic mass. So they're nothing but isotopes. So it has to be a thorium. An element is always defined by its atomic number. If the atomic number is same, I cannot write thorium here because it's 88 and 89. They can't be thorium. But I don't know what is them. But I'm interested only in my final answer. My final answer is 90, and 90 has to be thorium because it's same atomic number, different atomic mass. Okay, let's try this one. The element uranium has an isotope this much. Okay, fine. What is meant by isotope? Okay, we know that by now. Just same atomic number. Why do they have same atomic number? Is because they have same number of protons and electrons, but different mass number, because you don't need to write that, but because different number of neutrons. So one might have an extra neutron, and which would make it unstable, more neutrons, unstable. Okay. Determine the charge in coulombs of the nucleus. So they want the charge of the nucleus. What charge does a nucleus has? A nucleus has only protons and neutrons. So the charge is because of the 92 protons. So there'll be the charge on one proton, your data sheet has it, is this. Now, if you write a negative, you are not going to get that mark. Remember, the nucleus only has a positive charge. So just using my calculator here. Okay, just doing, wait. So 92 times 1.6 times 10 to the power minus 19 is, I'm getting 1.472. So I'm just writing it as up to two significant figures, 1.4 times 0.47. Sorry, that's it. Okay, let's do this one. A positive ion of uranium, so now it's talking about an ion, now it's not talking about the nucleus, okay, has charge of plus 4.80. That means it has more protons, isn't it? An ion, when it has a positive charge, that simply means it has extra protons. How many extra protons? Let's just find out. So if it has 4.8 times 10 to the power minus 19, and you divide it by the charge of, so 4.8 times 10 to the power minus 19 coulombs, if you divide it by the charge of one electron or one proton, this is what you're getting. So 3 electrons. So it has lost 3 electrons. That's why it has a plus 4.8 charge. So how many electrons would it have? If it would not have this, okay, let's consider a uranium atom. If it is a uranium atom, it'll have 92 protons and 92 electrons. What's the charge? The charge is 0. The net charge is 0. But this one says it has a charge of plus 4.8. That means it must have lost how many electrons? It must have lost 3 electrons. That's why it has a charge of plus 4.8. So the total number of electrons it would have is then 92 minus 3, that is 89 electrons. Okay, so if you have not understood, pause, rewind, redo it. Let's do the next one. U-237 decays by a beta minus emission. Okay, complete the equation for the decay. So whenever it's beta minus, let's look at, okay, what is for the beta minus? You have an antineutrino, atomic number increases, mass number remains same. Okay, this is what you should be doing, going back if you are not getting it. I'm just trying to model the way you should be working. Okay, so you have add in the values. Whenever a beta minus comes out, an electron comes out, this increases, so this becomes 93. This remains 237. This is because this one has a -1 here and a 0 here, no mass number, and this one is antineutrino. All right, okay, so this is the answers. All right, okay, now let's just see. An unstable nucleus can decay by emitting a beta minus particle. So it is decaying by emitting beta minus particle. What part of the atom is same as beta minus? Okay, we already know that is nothing but an electron. State the changes when X decay. So my unstable, okay, so this should be an X here. So unstable nucleus was decaying by beta minus. So change in A is a mass number, no change. Z is the atomic number, increases by 1. In the process of beta minus decay, an antineutrino is also released. Give an equation for this decay. So now you need to give the equation for the decay. So we can write a neutron changes to a proton plus beta minus. See, it has to be balanced. On your left hand side, neutron has no charge, but proton has a positive 1 charge. This has minus 1, so the total charge is 0, plus an antineutrino is released. Okay, that's a symbol for antineutrino. What is it? We're going to learn that in the next video. So that's your equation. Okay, now let's do the next question. An alpha particle is the same as a nucleus of the helium. All right, we know that. So this is what? Thorium, emission of alpha particle. Now, by all means, pause the video and try to do it yourself. If not, let's do it together. Or you've done it, you can check your answers. So if it is alpha, this is 2 and this is 4. So this should be 88. And this should be 229 minus 4 is 225. So X should be 225 and this should be 88. The mass of radium nucleus and the mass of alpha particle. So the mass of radium nucleus will be because of 225 nucleons into mass of nucleon, which is same as that. So if I just take the ratio of the mass numbers, that is what is going to give me the ratio of the mass, because the nucleons will have the same mass. The proton and neutron has the same mass in radium as it has in alpha particle. So the answer would be 225. You can always convert it into decimals. Okay, that's 56.3. Now let's do this one. Again, pause and try to do it yourself. By now you should be able to try it yourself. If you have done that, you can check your answer. Determine the charge. Again, we are determining the charge on the nucleus. Do not make that mistake. On the nucleus has only 92 protons, so 92 times 1.6 times 10 to the power minus 19 coulombs. Do not add a negative. Nucleus has a positive charge. This would be a 2-mark question. A positive ion with uranium nucleus has a charge of this much. So again, I think it's the same question that we did. So again, it has a charge of this. That means it's a positive charge. So the number of electrons it has lost is times 10 to the power minus 19, but it's 0, so I think I'll have to take another one. Say this will give you the number of number of electrons it has lost, which we saw it was 3. So we got 3 electrons. So that means it must have lost 3 electrons. So you should have 89 electrons in it. A U-239 nucleus decay by emitting 2 beta minus to give a plutonium. Pu is plutonium. State what X and Y represents and give the numerical value of each. X is mass number. Okay. Mass number or nucleon number, which would be 239, because in a beta minus decay, the mass number, don't write it, mass number does not change. And in Y is atomic number. In beta minus decay, Y increases by 1. Because there are 2 beta minus, it decreases by 2. So this is atomic number, and that would be 92 plus 1 plus 1. Why I'm writing 2 times plus 1? To make you understand that every beta minus decay atomic number increases by 1 for 2 beta minus decay. Okay, let's just see the mark scheme. There you go. So X is the number of nucleons, nucleon numbers, or number of neutron plus proton, or mass number. Any one of them is okay. Y is the number of protons, and it has increased to 94. So 94 gets 1 mark, and atomic number gets 1 mark. For the previous one, that's what is the charge. How many electrons are in the ion? So we got that 89. I don't. Why? Okay, we have it 89, and the previous one was, we did not write here, so 1.47 times. I'm just going to take it from the mark scheme, not using my calculator, but I think you got it. So, and that's what it is about. So whenever it's an alpha decay, going back, if it is an alpha decay, remember the mass number decreases by 4, atomic number increases by 2. If it's a beta minus decay, mass number remains same. In all the beta decays, mass number remains same. Beta minus increases by 1, beta plus decreases by 1. It's other way around. When it's plus here, this decreases because it's plus here. If it is minus, it increases by 1. Okay, so that's all. Next topic would be about the kind of particles and photons and a little bit quantum physics. So keep learning. Well done for today. Bye-bye.